So let's have a look at the next one. I hope you can see this. Is that if, of course, we have a circuit and there just happens to be two batteries, and this one, it might be again 5 volts. This one may also be 5 volts. We can see that they're both connected positive, negative, positive, negative. So conventional current is going to be pushed around the circuit in that direction. And so because these are pushing conventional current, if you like, or pushing or repelling electrons away that way if you want to do it that way, but conventional current going around that way is that they're both pushing the same way, so it's just 5 plus the 5 equals 10 volts. As easy as that. Alright, let's have a look at another one. So what happens if it's drawn a different way? What if you've got a circuit where you've got a resistor and you've got two batteries like that? Again, 5 volts, 5 volts. Well, it may not look very clear, but to start with, we should be able to see that again, this one's pushing conventional current this way, and this one is also pushing conventional current that way. So they're both pushing in the same direction, and so we get the effective EMF into that circuit is, let's write it like that, is 5 volts again plus the 5 volts equals 10 volts. That's okay. And you'll know from, just to take it a bit further, you'll know from Kirchhoff's second law that the sum of the EMFs into a closed loop equals the sum of the PDs dropped across components. So that would mean also that we'd have 10 volts across there. So it's the same circuit, but we can sort of draw it also as if you had the batteries connected like that and the resistor there. And so if there's 10 volts across there, just at the bottom, we would also have, that's our EMF, then we would have a PD of 10 volts there, because those two things are in parallel. All right, let's have a look at another one. So that's all great if the batteries are in the same direction. What happens if they're not? So what if, let's have a look at it simply, if we had, I don't know, a 10 volt battery that way, and then we also have a 5 volt battery that way, and again, whatever, we'll just have a bulb in this case. Well, this thing is trying to push this way, push electrons this way. This thing is trying to push electrons, well, conventional current, shall we say, that way. But this is 5 volts and this is 10 volts. And so we do just treat it like a vector, is that if you've got something pulling this way with 10 and this is pushing that way with 5, then it's the difference between the two. So we can think of this as being plus 10 volts, and we might think of that being in the opposite direction, so being minus. And so the EMF would be 10 volts minus, or even plus the minus 5 volts equals the 5 volts. Okay, yeah, if they're in opposite directions. All right, let's just have a look at one more in case it looks slightly different. Imagine you had, again, 10 volts, a resistor there perhaps, and then another battery here, 5 volts. And guess what? What's going to happen? So this is going to try and push conventional current around there with 10 volts. This is going to try and push 5 volts that way. And so what would we have? Again, the EMF in this case would also be that 10 plus, and again, we might suggest that because it's the other direction, we can call it minus 5 volts. 10 minus the 5, yeah, it's an EMF of 5 volts. And again, if that's an EMF of 5 volts, then Kirchhoff's second law suggests that this would also have 5 volts across it. The sum of the EMFs, taking the sign into consideration, is equal to the sum of the PDs. Okay, hope that's a little bit useful.